So my name is Mike McBride. I hail from about an hour south of here in Orange County. It's a completely different world than LA. It's oftentimes referred to as the Orange Curtain. It's very much more conservative than the more liberal LA, and I don't get up here all that often, so it's actually kind of nice to make the trip up. I've been with Cisco Systems for 15 years now. It's much longer than I ever thought I'd be with the company. And during that time, I spent a lot of time in the initial years in the Technical Assistance Center. Then I worked in many of the years in the Multicast development group, doing a lot of testing and architecting, and that's what I do today. There's a lot of technical leaders at Cisco, and I'm one of those. So I spent a lot of time working with service providers, particularly on the IP multicast side. I also spent a fair amount of time in the standardization. I work with a good guy named Stig Venas, who lives up in Norway. We together co-chair the PIM working group within the IETF. I realize some of you couldn't give a flip about standardizations, and some of you do. So part of the presentation, I'll talk about some of the standardization, where we stand with, there's a lot of protocols when discussing multicast, particularly with regards to IPTV. And it's primarily in the IETF. There's a lot of standards organizations, the ITU, TISPAN, DSL Forum, which is now the Broadband Forum. But the IETF is primarily where we focus our efforts, and that's primarily where the standardization of multicast is occurring. So let's proceed. I'll do my best to keep it to an hour and a half. We'll just stop at an hour and a half. And feel free to ask questions either during or feel free to come up to me afterwards. I'm not in any particular hurry to get home. And so let's make sure you understand this content. So this is the goal, to provide you with a thorough understanding of IP multicast, particularly in use with IPTV networks. There's a lot of protocols involved. And I wish I had a remote clicker. All right, so here's the agenda. I'm not going to go through each of these because we're going to start going right for it. So let me give you just a basic introduction. All right, we're good. Okay, I will ignore you. On IPTV and multicast, hopefully most of you are pretty familiar with the technology. If not, we'll just give a really basic overview. So this is just kind of a common marketing slide that's used just to kind of help us understand really what multicast is all about, particularly for IPTV delivery. And what it really is all about, particularly on the bandwidth side, is the ability to just send the video into the network once and let the network handle the replication. So if you have 1 million users, that's significant. If you're sending that via unicast, you have to use other mechanisms to send that many times and a lot of servers. With multicast, you don't need that. Which kind of leads me to this next slide, which I thought was somewhat hilarious. And I just had to put it in there. I do it somewhat tongue-in-cheek. However, if back home you need to somehow, if you're not using multicast today and you need to persuade those back in your companies that really multicast is really the technology that we need to use, feel free to use this because it is a green technology. You're able to save on the amount of servers. You can save on power, save costs. I'm somewhat surprised we have this many people in this room. I thought there would just maybe be a couple people because of the economy, and it's been a bit of a nightmare the last few weeks. And so it can help reduce a lot of things. So it's a little tongue-in-cheek, and it's a little bit cheesy, but in a way it actually is correct. So when we're talking about broadcast IPTV, we really are talking about IP multicast. Whether that's on the network side, and we're going to spend a lot of time on the network side, particularly the transport part of the network. And that's also true with the host side, the senders, you have the encoders and the head ends, you have the set-top boxes and the receivers. They're using multicast. And of course, you've got it on the network side as well. And beyond just the sources, the encoders and the receivers, you have a lot of other devices that also need to be able to be multicast capable. You've got the groomers that are taking a variety of streams and putting them into whatever available bandwidth we have. You've got ad splicing, where the stream's coming in and you're changing that stream and inserting local commercials, for instance. We're primarily here in North America referring to this as an IPv4 technology. We have deployments where there's millions of end users and they're using IPTV in IPv4. We do have some deployments in Japan using IPv6. We've had that for a few years as well. All right, so the strategy and the recommendation, and these first several slides are going to be fairly high-level architecture type slides, and then we're going to get into some nitty-gritty. For those of you that like nitty-gritty, then we're going to delve into it. And then we'll get maybe a little bit higher level, and then we'll delve into it again. It's going to be a little bit wavy. So if you don't already have multicast in your network, you need to, of course, add that into your network. And that really needs to be SSM. I'm going to talk about that in more detail, but PIM-SSM really was created for IPTV. There's a lot of other PIM modes out there. There's sparse mode, there's PIM bidirectional PIM, and even dense mode many years ago. But SSM is really what we need to use for multicast. If you already have it, you really shouldn't need to do anything different with what you've already deployed. You just may need to add some additional capabilities to your end host. We'll see where that is. And then one of the more important decisions is to choose the transport method in your core. You have a variety of choices. You can either natively transfer multicast, or you can do it now with MPLS-based label switching of multicast packets. We'll talk about that in a fair amount of detail. You can also do layer 2 forwarding of multicast traffic, or you can maybe do a mix of both. And then you have a variety of IPTV services that all hinge upon multicast and the protocols that make up multicast. And you're just going to typically start off with traditional TV broadcast, whatever available channels there are, and now allow it to go across your IP backbone. There was paranoia before of allowing multicast to transit your national backbone. And we've proven that that's something that you don't need to be paranoid about. It works just fine. And the more services you're able to offer, the more return on investment of your network that you can receive. So there's a variety of services that we can offer. Again, I've mentioned groomers and other technologies on the host side. There's switch digital video, which we'll discuss a little bit. There's other services as well that may even go beyond IPTV. With regards to MVPN, you can have pre-positioned video on demand, which is done using unicast, not multicast. And in addition to that, you can have multicast in your internet space, which many of you probably already have in your networks. Multicast has been something that on the internet side, service provider side, has been somewhat uninteresting. There's been, you have the Internet 2, which on a daily basis is forwarding multicast content. There are some business models that base a business model on streaming of multicast across the internet, particularly audio. But there hasn't really been this killer application on the service provider side like there has been on the enterprise side. In the financial world, they've heavily relied upon multicast for many years for their stock information. And it hasn't really been until having IPTV transit a provider core until really starting to get this killer application now. And there's a lot of details behind that and that we're going to get into. So still a little bit at a higher level, we have this network. You've got all your routers and switches and all the protocols that make up that. You've got your multicast routing protocols. You have your unicast routing protocols that multicast is heavily reliant upon. And then on the host side, on the services side, you have all the complexities involved with what revolves around the hosts. You have, again, you've got your sources. You've got redundancy necessary for your sources, for failover. On the set-top box side, there's a lot of details and protocol complexity there. But there is this service interface between the two that you need to understand. So you have two different camps, and sometimes they kind of stay in their own worlds. But we have this service interface where sometimes they need to start understanding each other's worlds. Particularly on the host side, when they are needing to have a certain type of service made possible from the network side. They have a certain expectation of quality of service. And so they need to be aware of what's going on in the network. And the network needs to provide the resiliency necessary for that video stream to quickly fail over in those cases and to stream appropriately. So I've mentioned that there are these different layers. There is the network side. There is the IPTV side. You have a lot of different complexity and specialties. Across those, you have IP multicast. So you may just think, you know what? For instance, I've got an optical network. All I'm doing is transiting packets. I don't really need to understand the complexities of multicast. Well, if you need to understand the service, particularly end-to-end, you really do need to understand multicast. And if you're on the host side, it really could do you well to understand multicast and how all the different signaling is used. So I mentioned SSM. That really is the PIM mode that we need to use that was primarily developed for IPTV, where you have a source that's running IGMP version 3, which now is able to request a particular source and group. I got a few slides coming up that talk about this a little bit, but prior to SSM, we have what we refer to now as ASM, any source multicast. So when a host joined a particular group, they're going to join any sender for that group. You could have multiple senders sending to that same group, and it's going to receive those. You could even have some sort of a denial of service attack against that stream by just sending to that same group. With SSM, you don't have that because the host is now requesting a source and a group. So we refer to that as a subscription to a particular channel rather than just a join. So we'll get into some more of those details as well with some diagrams that make it all pretty. And also, it's important on the network side to have the necessary redundancy. So if there is failover, we can quickly get over to the next stream so that there's a good quality of experience for the user. Because that's really what the paranoia was of having your broadcast TV go over an IP network, is just that you want the viewer to knock it off their couch and give you a call. You want them to have a good experience. And so they had so many years of not using IPTV where they had a good experience. And so now we're adding the video to your IP network with all the available services that we can add to that, and we need to make sure it's a good experience for the user. And so one of those ways is to provide appropriate emission control. You can use RSVP to do that. You got multicast emission control, which I'll discuss to make that possible. It's mostly based upon CLI configuration, but there's also some other options as well. Of course, management and troubleshooting tools are all available. So if you own the network and you're working with the IPTV services side, it would behoove you to try to find a way to make SSM mandatory in your network. So when they connect up to your network, you can say, you know what, we're using SSM, we've got to use that, that's our choice, so you need to have IGMP version 3 capable hosts. There are some workarounds to that if they don't, or maybe you can work out a transition plan. There's something like SSM mapping, for instance, that allows a host that's maybe running the previous version of IGMP, which is IGMP version 2, where they're just requesting the group, to go ahead and send IGMP version 2 requests to the local router. And the local router, if it's running SSM mapping, can then convert that by using some out-of-bound mechanism, such as DNS, to find out what the address of that source is, and then send SSM throughout the network. A lot of details and a lot of protocols to understand. So one of the key choices, as I mentioned before, is you need to decide what your choice of transport will be in your backbone. You can either do it natively using SSM, or you can use MPLS, label switching and multicast packets. The two ways to do that the IETF has converged upon is MLDP and point-to-multipoint RSVP-TE. So LDP previously was point-to-point. If you add the multicast component to that, you'll now have replication and you have point-to-multipoint LDP. And I'm going to show you a flow diagram and exactly how this works step by step, including with RSVP-TE point-to-multipoint. Path selection is very important. You need to have a fast way of rerouting. Of course, if you're already running RSVP-TE, you understand the traffic engineering benefits of that technology. And so you can traffic engineer optimizations around failures, which is key when you're talking about broadcast video. And Of course, with virtualization, with VPN, you have the capability of using L2 VPNs or L3 VPNs. And we're going to spend a fair amount of time on the VPN side as well, since that's been a big win for service providers with Multicast. All right, so let's kind of somewhat quickly go through this since I've kind of already talked a lot about it. We do have a lot of protocols on the Multicast side. If you're not familiar with Multicast, it can get very overwhelming. You got PIM sparse mode, you got MSDP, MBGP, AutoRP, BSR, et cetera, all the LSM protocols. And sometimes a fair amount of complexity. And this, of course, you understand how it works. And then you have the services that rely upon those protocols. And those services that we refer to are typically, again, any source multicast and source-specific multicast. Those are really of the most interest to us. On the host side, you have IGMP, and you have different versions of IGMP. ASM has been around for a long time. That's the RC for the host side. RC 4601 is the RC for PIM sparse mode. We finished that a couple years ago. And then source-specific multicast has been around since about 2000. Again, primarily introduced for IPTV services. Some of you that are long-timers and understand multicast for many years are familiar with DVMRP, Distance Vector Multicast Routing Protocol. It was a very PIM dense mode-like protocol where it flooded throughout the entire network and then pruned back. It had its own routing protocol integrated as well. That's old technology, and we've even been removing that from some of our platforms. So if you're using DVMRP, it's time to move on to get something such as PIM SSM. And then again, we've had all these protocols, which PIM sparse mode has been a very good general purpose routing, multicast routing protocol. It's what's most widely used today out there in the networks. It's just that for IPTV, SSM is really what you need to do. I mentioned that with ASM, it's a little bit easier to have denial of service attacks. With SSM, that's not a problem. At least it's much harder to spoof both the source and the group. Address allocation is also of a concern on the ASM side, where on the SSM side it's not. You could have two sources sending to the same group, but since they have their own unique source address, that uniquely identifies that stream. So there's not an address allocation problem. So I kind of mentioned this as well, kind of a historical look at a typical distribution of IPTV across the network. So the old designs have used a non-IP satellite distribution, inject that traffic either in the access layer or in the aggregation layer, or just use regional local content and just inject it wherever you need to have that, just locally, and just keep it off the national IP backbone. But the current designs do use the national IP backbone for distributing that content, and again, it scales just perfectly. So let's take a look at this in a little bit more detail. We have a typical L3 aggregation type of a network for IPTV running multicast. So we have our set-top box on the right, and we have our head end over here on the left. Set-top box, and you have the multicast signaling on below that kind of shows you what's going on. So up to that aggregation router, that's where we begin our L3, from there to the left. Before that, to the right, is on the layer 2 side. So we're talking about IGMP on that side. So the set-top box is sending joins using IGMP versions 3, requesting a particular stream. That gets propagated up through switches. Maybe you have a router over here on the home gateway that's doing proxy routing, and I'll discuss that in a minute. I'm going to leave a question mark for the broadband side just for now. We'll look into that into more detail in following slides. But you have this aggregation router who now is beginning to use layer 3, and it will now send these SSM joins into the network to request particular streams. What typically is happening today is that you're statically joining those across the backbone, so that all the content for the channels is automatically getting sent to the aggregation layer, and it's receiving the content, and it's only sending it out when it receives the IGMP version 3 joins. Again, there's a lot of options for your transport in these clouds over here. We're going to discuss those in a fair amount of detail. Again, you can use SSM, you can use label switching in multicast packets if you wish. You can use VPNs, multicast VPNs. And then on the head-end side, it's important to have some redundancy there. So if one source fails, you can quickly fail over to another. And the network also needs to support that, so that if one failed part of your network, if one side of your network fails, you can quickly optimize over to the other side of your network so the viewer doesn't see very little of a artifact in what they're seeing. All right, so let's dig into a fair amount of detail on the transit side. I'll try to keep it as understandable as possible. Again, if you're familiar with multicast, this will be fairly plain. Some of you I know are already running these technologies because it's been deployed in many large Tier 1 providers. But if you're not familiar with multicast, it can get a little overwhelming, but I think I can make it somewhat understandable. So again, we have SSM or MVPN. Those are really the common deployments as a transit technology. And so there's support for things such as MPLS multicast label switching. I've mentioned MLDP, which is basically PIM with labels, as well as point-to-multipoint, RSVP-TE. Again, that's as opposed to what is occurring for unicast, where you have point-to-point tunnels. We now have the ability to replicate and have that go into point-to-multipoint fashion. And we can use that into VPN context. There's some PE to PE signaling that needs to occur, and I'll try to make that clear. One of the important things to understand is that on the customer side, they're using PIM. So we have CE2, CE3, and CE2 over here in the content source, receivers on the sides. They're using PIM to do their joining and sending of multicast traffic. And then you've got this core here, PE1, PE2, and 3, that also needs to decide how they're going to do their multicast tree building. They can either also use SSM if that's what the customer is using, and that makes it pretty simple. Or you can use multicast VPN if you need to have a VPN. Or you can just label switch that multicast. So you can use PIM to create trees in the core. You can use MLDP to create trees in the core. Or you can use point-to-multipoint RSVP-TE to create trees in the core. And there's also some optional PIM or BGP extensions as well for the P to PE signaling. So I mentioned what's currently widely deployed. We have what's currently widely deployed. We have SSM, and that's pretty straightforward. On the MVPN side, that has been a big win for many service providers because they've needed to find a way to transit their multicasts over their provider backbone for their VPN customers. The VPN customers are screaming, hey, I got these VPN sites, but I'm not able to get my multicast from one site to another. So we've had this PIM-based MVPN solution for several years now that's been very successful, and it's something I'm going to talk about right now. So you got this gentleman here scratching his head, trying to find a way to get his VPN traffic to support multicast from one site to another. In RFC 2547, there wasn't a specification for allowing multicast to be label switched across the core. So we couldn't actually allow multicast to go across an RFC 2547 MPLS-based core. So what we had to do, some of you may have been there, is create tunnels, which is not very fun, from CE to CE, just to tunnel over it and just to hide the MPLS core. Obviously, it doesn't scale very well. With multicast VPN, and we're going to talk about this PIM-based solution, and then we'll also talk about using RSVP and MLDP as well. But the basic concept is you have these different customer sites. We have a blue customer and a red customer. And what we're going to do, it sounds kind of funny, but we're going to encapsulate multicast in multicast. So when a multicast packet comes in from a customer, what we'll do is we will encapsulate that in a new multicast group destination address. That destination address will only be used for that particular customer. So for the blue customer, I'm going to use 239.1.1.1. So whenever a multicast packet comes in, I could have 1,000 streams coming in from this customer, but I'm going to aggregate that into just one tree that will go to all the VPN sites, and the destination address just across my core will be 239.1.1.1. and then I'll decapsulate it and send it off in its original source and group address. So there's two types of multicast distribution trees, MDTs. There's a default MDT and a data MDT. In the previous slide, I showed you the default MDT, where for each customer, you have this tree. It's going to lead to each of the VPN sites for that particular customer. And that's specified among many other options in this 2547 BIS multicast draft. So if you want to read a huge document that specifies all the different options that I'm going to discuss today, including this PIM-based MVPN solution, you can look at that document and read that. So there's a new term now for default MBT and data MBT. It gets a little confusing. I'm going to continue to use the older non-standard terms because that's what I'm used to. But for default MBTs, it's now referred to as a MIPMSI, Multi-Directional Inclusive Provider Multicast Service Interface. You can probably see why I like to use just the default MBT. It's a little bit easier. It rolls off the tongue. But it makes sense because it's a service interface providing for the customer. It's just providing a service that I'm going to allow your multicast to enter into my network, and I'll provide you a service to go to your other locations. And you can optionally configure a data MBT, and this is going to all be made clear in some diagrams I have coming up. And this makes things a little bit more efficient. So let's take a look at this. So for this blue customer, we've provided a default MDT. We have a receiver on the bottom left, and we have a source on the right. Do you guys have these slides? Or, is it online or something? Or is this... No? Yeah, it is? Okay. So I hope I'm not getting in your way here. And you have the source on the upper left-hand side. So receiver joins. It wants to receive this packet up here from this source. A lot of packets from the source, this stream. So it's requesting 192.2.2.2. The destination is 224.0.0.13. Actually, that's its own source and destination. What it really wants to join is 192.1.1.1. That's in the payload, and 239.255.1.1. So it's joining for that particular group up there. Its own address is 192.2.2.2, and it's sending it to the all PIM router's address. So what does the network do? So this PE running MVPN, PIM-based MVPN, will encapsulate that in a new multicast packet. The source will become its own address, 10.2.2.2, with the destination of this new multicast group, 239.1.1.1. It's the address used only for this VPN customer blue. It will go to all the VPN sites. So that's what it does. And then when it leads to the PE up here leading towards the source, that PE will decapsulate that and send its own join towards the source, requesting that group that this receiver down here below wanted to get. So the traffic begins to flow. So the PE up in the upper left-hand corner will receive the traffic. It again encapsulates it into a new source and group address, only used for this particular VPN and only used across the core. And then that PE leading towards the receiver will decapsulate that, and it's sent off in its original 239.255.1.1, the same group that's up there in the upper left-hand corner. So again, it's just an encapsulation method. And it's nice in a way because, again, you can have a lot of sources from your customers. And you don't really care how many they have because you're just going to aggregate it into one group. So in your core network, you just have one state. They could have hundreds of different multicast S and Gs. You're just going to have one. However, there are some advantages and there's some disadvantages. The advantage is what I just stated, is it reduces state in the core. The disadvantage is it can result in wasted bandwidth. That PE in the upper right-hand corner doesn't have interested receivers. If that's across the ocean, that's a lot of wasted bandwidth, particularly for an IPTV stream. Several megs of information. So some customers prefer to make it more efficient. They prefer to take the hit in state and make it more efficient. So you can optionally configure what's referred to as a data MDT. or a selective provider multicast service interface. So we have the traffic flowing on this default MBT. Everybody's happy, except this router in the upper right-hand corner who's getting hammered with this traffic and doesn't want it. So what the PE router in the upper left-hand corner can do when it's configured is it can configure a threshold. It can signal a change to a new group, saying that if you're interested in continuing to receive this stream, please join this different group. So the PE routers that are connected to receivers will send a control packet saying, yes, I am interested in this group. And so I'm going to join a new group, a new encapsulation between PE and PE. So what we have now is we have two states in our network for this particular customer. We have the default MBT, which continues to be up and running now, but it's not getting hammered with this IPTV traffic. It's just staying up for control traffic. If there's any new sources or new groups that need to come up, it will be there. But the traffic is now just going from the source towards the receiver. Again, you now have additional state in your network. There's one particular tier 1 that's very paranoid about having multiple states in the network, so they don't do this. And there's some others that are not as nearly as concerned. And so they're not as concerned about the amount of SGs in their network. So this just takes a look. You can look at this a little bit later to just kind of go through it in your mind how this encapsulation works. But you're just changing the source and group address and then putting it back after decapsulation in its original form. So that's MVPN, PIM-based MVPN. And it's one of the many ways you can build these tunnels in your network. So additionally, you can also create these trees not using PIM at all, but using label switch multicast, using MLDP or RSVP-TE. Or you can use a combination of them if you wish. And they each have strengths and weaknesses. But it's something that you need to be aware of. So let's kind of get into the multicast part of this. The label switching, rather, part of this. So in MPLS traffic forwarding of multicast packets, whether you're using MLDP or point-to-multipoint RSVP-TE, the forwarding is the same. The hardware requirements with both are going to be the same. It's just a different way of setting up the tree. For those of you that are familiar with the label switching world, with multicast there is no penultimate hop popping. We need that label all the way to the edge so we can identify the tree. With unicast side of that, you have two labels, both for IGP and BGP, and you need both labels. After you pop the IGP, you still need the BGP label. With multicast, you just have that one label, and you need that. So there's no PHP. So let's just take a look at this. Okay, so now we're talking about label switching and multicast traffic. We're not talking about MVPN. We're just talking about this, and we're not using PIM anymore in the core. We are using PIM on the edges to request certain traffic, but we're not using PIM in the core. So what happens? We have this route. Each of the routers either statically are configured to that, or they're learning about it through a dynamic out-of-band mechanism, either BGP or some other mechanism. So when the PE router, PE2 in this case, receives a join, it's a regular PIM join, what happens? Well, what it will do when it's configured for MLDP is it will dynamically encode an FEC. Now, this is somewhat of an unfortunate name because in the video world, of course, we have that term already being used for forward error correction, which we'll discuss. It doesn't mean that in this context. It means forwarding equivalency class. It uniquely identifies this particular stream. And so what we have it identifying is the route. It identifies the source in the group as well as the route descriptor. So all this, the FEC is variable length, so we can add all sorts of values to it to identify the stream. So that PE2, upon receipt of that, will create an LFIB with multiple outgoing labels. And that's kind of really the magic of this, is having labels going out multiple interfaces rather than just in a point-to-point fashion. So it'll build that and then advertise its own label up towards the route. The route will decapsulate that and send it off in its original IPv4 packet. The content source and this other router over here will do the same thing. The source will begin streaming. So what happens? Well, that PE2, that PE1 router over here, this root router, will push a packet with a label towards PE4. PE4 will swap and replicate that out multiple outgoing labels, in this case 20 and 30. PE2 will get that, and they will pop that outer label and reveal the packet inside. So it's actually fairly straightforward if you already understand the mechanisms of LDP. It's very dynamic PIM-like version of it. It's really kind of the best of both worlds between PIM and LDP. So that's a non-VPN environment. We can also use this for VPNs, as I mentioned, as another way to build trees. You're going to derive your FEC from your configuration. And so let's take a look at this. So as the labels begin to flow on the left-hand side, we've got the traffic coming in. We'll push two labels now into the network. The outer label will be used by MLDP. The inner label will be used to identify the VPN. PE4 will swap or replicate those out multiple ports. PE2 and PE3 will pop the outer label, the outer MLDP label, to reveal the VPN, and then they'll pop that to reveal the V4 packet. So that's MLDP. You're able to take advantage of the LDP capabilities of TCP. It's very dynamic. You'll see with point-to-multipoint RSVP, it has many strengths, and the way that you configure it is it's very head-end driven, pre-positioned and statically configured to work through your network. And this is the alternative to that. It's, again, very dynamic. It's very PIM-like. And you are avoiding some of the potential complexities of PIM. You don't have your rendezvous points, designated routers, and asserts, and other potential complexities. So on the point-to-multipoint RSVP-TE side, again, the forwarding is very similar. Extensions have been made to RSVP-TE to allow it to replicate out multiple labels, multiple interfaces. Label requests are done in the path messages, and label bindings are done in the reservation messages. And so we have all the capabilities that are within RSVP, but now we have the capability for multicast, the point-to-multipoint. Point-to-multipoint RSVP-TE is an RFC. It's more mature than MLDP. It's just not something that we're as familiar with because it's not as PIM-like. It's, again, statically head-end configured. And so you have a label merging occurring in the middle of the network, in this case anyway. And otherwise it's very similar. But it's just another way to set up a tree in your network in addition to MLDP and PIM. And RSVP-TE does have a lot of strengths. And we're going to talk about some of those as we show some other details as far as re-optimizing throughout your network and link protection and all that. All right, so I'm going to hopefully go through this a little bit quickly. But there are some benefits, as I mentioned, of PIM and MLDP over point-to-multipoint RSVP-TE, and there's benefits of the RSVP-TE over PIM and MLDP. One of the benefits of MLDP over RSVP-TE is the cost of the trees. If n equals the number of tail end PEs, then with PIM and MLDP, we really have a cost of 1. With RSVP-TE point-to-multipoint, it's n, because the more receiver PEs you have, the more head-end configured, statically driven trees you have in your network. So it's proportional to the number of PEs that you have. So the cost of trees is more with RSVP. Some people may say, so what? And they may be right. Also, locality. This may be a little bit hard to understand, but let's just focus on this purple circle right here. We have these 3 routers. And if we have a link failure with MLDP and PIM, you'll optimize around that and fail over to another router. And a failure will really only affect those 3 routers. Whereas with RSVP-TE, point-to-multipoint, other parts of your network will also be affected because you have to re-optimize from the head end. You have these point-to-point sub-LSPs with point-to-multipoint RSVP-TE, and so those all need to be re-optimized. So that's a little bit of a difference as well. RSVP-TE benefits over PIM. You have this sub-50 millisecond protection. And that's really one of the main reasons that people are using RSVP to begin with, is because of that very quick failover. You can also very easily load split traffic across alternate paths. I'm going to discuss Live, which is a very important piece of streaming IPTV across your network. And RSVP-TE does this nicely. You can have 2 different diverse paths in your network. And if one fails, you can have that fail over to the other side of your network on a different part of your network as well. And it also can sometimes help with loss in certain scenarios. You can also combine them. That seems like a little bit interesting to do so. You can also have them work in a ships in the night kind of manner. But what you can't do is having LDP signaling to a RSVP-TE core and then signal back to LDP for a particular tree. Maybe someday we'll need that. You can do that in unicast today, but right now they would be something that would be ships in the night if you want to get really creative. How about layer 2 VPNs for multicast? Unfortunately, in the standards world, L2 VPNs for multicast isn't standardized very well. There are some informational RFCs and a variety of drafts trying to help make that work. There's a lot of interoperable concerns with IGMP snooping, and there's really not a dynamic solution using point-to-multipoint trees. VPLS is defined, and that's working. But typically what we recommend for most customers is to use an L3 VPN solution and the abilities that you have there that I've already discussed and that I'll continue to discuss, and more control of your traffic. And typically what we recommend to customers that are really needing to use L2 VPN is to, if you need to have VPN sites partitioned, rather than just have that traffic go to all your VPNs, then you may just want to sell a new L2 VPN, multiple L2 VPNs for that particular customer. So here's a summary of all the things that I've discussed. Transit options, there's a lot there that I just discussed. You could probably have a couple-hour, actually you can very well have a couple-hour presentation on each of those technologies. But hopefully that gives you a little bit of a flavor of the technologies that are available in the, on the core side. A lot of choices to decide from. But the nice thing to know is that they're working, and they're working well. All right, so what about the broadband side for IP multicast? In the previous slide, I had a question mark in that, so let's take a look at that a little bit. So, again, you can have on the aggregation side, that could be where you begin your layer 3 multicast. You can have IGMP memberships going up to that. We could be using a DSLAM, for instance, that's just forwarding those IGMP version 3s up towards the aggregation router, and then have your joins occurring from there, or you can statically configure all the IPTV streams, the channels, to be forwarded to the aggregation router, and then just waiting for the membership joins to occur before you forward the traffic. Or you could extend that layer 2 side even further, all the way to the core distribution router. So you have a very large layer 2 segment. And you would just inject that content either at the aggregation side from the head end or in the core distribution side. And you can see just that layer 3 is really just starting at the core side. So in all the cases, you're using IGMP snooping or IGMP proxy routing. So if you look at these two diagrams, on the right we have a switch and a router, and on the left-hand side we have a router and a router. On the switch side, let's say we have 200,000 customers. And they're all sending their joins and leaves up to the local router. And if that switch is just transparently forwarding those on, that router we don't really want to scale a router to be able to handle that many joins and prunes. Joins and leaves. We can make it, but I don't think you'd probably want to pay for it. So it's something that we need to try to work around. And we can work around that by using proxy routing. And you can do that in the switch as well as the router that we see here on this left. So if you have 200,000 subscribers, set-top boxes that are joining to particular channels, we can run proxy routing on that router or that switch to just send an aggregate. So if you got 50,000 set-top boxes joining a particular stream, instead of sending all 50,000 of those join requests up towards the local router and hammering it, you can just send one. I want this one particular channel. Thank you very much. And so that's what IGMP proxy routing allows you to do. And it is a standard track document in the IETF. How about the cable world, data over cable standards area? So this is non-DOCSIS. The next slide will talk about DOCSIS. In the something that's specified in, I mentioned the broadband form. It was referred to as the. Actually, forget that. This is something that's before. This is before DOCSIS. So we have our edge QAM here in this case that is sending the memberships. And then we've got this aggregation router that's sending the joins. Again, you still have the similar signaling. You've got your transport options that we've already discussed. We've got our head-end router. We'll talk about some redundancy options here in a minute. But this really, in some ways, is not really even IPTV because it's not IP all the way to the set-top box. You've got IP going to the edge QAM, and then from there it's just the regular broadcasting over the cable network. With the DOCSIS specification, DOCSIS 3.0, we really now have over cable true IPTV all the way to the edge because it specifies IP capability to the set-top box. And so with DOCSIS 3.0, we have really good multicast capabilities. It specifies using IGMP version 3, which allows for SSM in your network. And so it's been a big win for multicast, and that's coming. It's already been specified, but the support for it is coming. If you have a part of your network like let's say a DSLAM that's not multicast capable, it's not going to be forwarding IGMP traffic, then there's something that's being specified in the MBONE-D working group of the IETF, and that's automatic multicast tunneling, where you can dynamically route around non-multicast parts of your network. It's an interesting technology. It's available today if you want to play with it, and you can download code to your devices. All right. So how about resiliency? This is a cool topic. How about the failure impact upon the user experience? Sometimes that's hard to measure and quantify, except when they're giving you calls. If you're an operator of a service, they're getting off their couch and they're calling you saying, hey, either I'm losing my stream or it's taking me 10 bloody seconds to just change from one channel to another. That's, I guess, one way that you can measure the quality experience of the user. One of the reasons it's also hard to measure and quantify is because when you have a IPTV stream, which is a RTP over UDP over IP stream, and you have this encoding, and encoding is being done because if you're not using encoding, of course, you can have a gig stream, and you just quickly ham your network. You just couldn't support that. With encoding, you could take that gig stream and reduce it down to like 8 megs, for instance. So encoding is very important in the IPTV world. Part of that encoding is you have this group of pitchers, GOP as it's referred to. And in a group of pictures, and I got a diagram coming up here, you have what's called as an iframe. I'm sure many of you are familiar with this. And the iframe is a complete picture of the group of pictures. It's a complete reference point. And the subsequent frames in this group of pictures are primarily reference points to that iframe. You've got your P frames and your B frames. And so they're able to make it so that you can remove a lot of information out of this group of pictures, and so you can reduce the amount of bandwidth that's required. And then you can restore it on the far end side. So you're basically taking the duplication out and restoring it on the far end side. And so that's kind of the complexity that's involved with the set-top boxes and involved with loss and all that. Sometimes these group of pictures can be quite large. They can be, a lot of group of pictures. There could be maybe, I don't know what they are, like 30 maybe pictures. Whereas maybe the small inside, they're like maybe 8 to 10 pictures. And so if you're losing an iframe, that's why it's kind of hard to measure, because if you're losing an iframe, you're taking pretty much a major hit of the whole group of pictures. You have to wait for the next iframe before you can get a full reference point again. So in these kind of networks, you really want to try to reduce losing any packets at all, because if you lose an iframe, it could take 10 seconds before the quality returns, and that's not a very good experience for the user. So this visually depicts what I just mentioned. You can look at this later to kind of study it. You've got your iframes and your P frames, your predictive frames, and your B frames. MPEG-4 is able to compress even more than MPEG-2 because it allows the B frames to make references to one another. So not only is there a reference frame to the complete picture, the iframe, but you can also use a reference point from B frame to B frame. So you're able to even reduce more information out of that and compress it even further. So with all that fun stuff, there's really two schools of thought in deployments today. One is, I really need to have 50 milliseconds convergence, because I know that in the voice world, for eons, we've known that you need to have 50 milliseconds quick failover, because we've noticed that for the last 100 years, if you have anything 50 milliseconds or less when you're talking on the phone, most people don't hear that. 95%, I think, of the people will not hear any sort of a degradation in the voice quality if it's 50 milliseconds or less. If it's more than that, then you start noticing a quality on the degradation in the quality on the phone. Now, is it fair to take that over to the video, to make that a video requirement as well as 50 milliseconds? It may or may not be. In many cases, it may not be. You may not need to have a 50 millisecond requirement. In some cases, it may not be enough, because if you're losing, again, the iframe, you're hosed for several seconds, and the channel change times can be unbearable, and the quality can get bad. So where do we put the effort? And so that's the question of the day. Do we handle it on the application side, where we use something that's forward error correction, where we introduce a little bit of a delay because we're adding to the existing packet so that we can have compensation for certain packet loss. So on the application side, we can do forward error correction to correct for particular loss. We could do retransmissions, which in some cases works quite well, but for broadcast IPTV, that typically doesn't work so well, because by the time you're retransmitting, you're already losing the packets, and it's too late. And so that's not being used for IPTV solutions unless you're using something that'll share towards the end. So what about on the network side? Most of you are interested, what can I do on the network side to make it so that it's a good user experience? Well, from a host component side, from a source side, we can use a variety of different technologies to make sure that there's a failover from one source to another. Some of you may be using Anycast RPs in your network for multicast failover, where you can use the same idea, but we can use that for sources. And PriorityCast is a similar thing as well. What you can also do is you can use dual transmission in your network, and this is very successful. You can send the same stream in different portions of your network for path diversity. It's the same exact stream, but if one stream fails, the other stream is still being received, and you can start using sequencing, receiving that new stream without any hit at all. It's a hitless failover mechanism. That's a good thing if you have the bandwidth to handle that. So let's talk about the sources real quick. So there's a couple different approaches. One is a primary backup method of providing redundancy for the sources. And another mechanism is a live-live or a hot-hot, where you have two sources both sending into the network. There's no protocol necessary in a live-live, hot-hot environment. When you have a primary backup, there is some signaling that needs to occur between the sources, some protocol. So if one source stops sending and needs a signal to the other router, the other source rather, that it needs to start sending into the network. In a live manner, you don't need that. So there are some pros and cons of each. On the primary backup side, the functionality on the receiver is a lot more simple because it's just always just receiving one stream. In the live method, there needs to be some more intelligence on the receiver side. And that receiver can be a router or it can be a set-top box. But it needs to be able to know that, okay, I'm receiving two streams. I'm not receiving this stream anymore. I need to just quickly fail over to this other stream using sequencing. You can even do it so that if you have a source that's sending multiple streams out of it, different channels out of that one source, you can even use something like RIP version 2, for instance, to remove that particular route, that particular stream from your network, and you can fail over to another source. So this is a cute little way of looking at this. So you have these set-top boxes that are sending in IGMP version whatever, version 3 reports. And then we have these two different sources, both the same IP address, sending to the network. And so what happens is using Anycast-based load balancing, it's very similar, again, to the Anycast RP for a multicast network, is the aggregation routers on either side will, just using the IGP of the network, send those joins to the nearest instance of that source. And so it will just use that part of the network that leads towards the nearest source. If one source fails, then what will the network do? Well, the IGP will just recalculate, and the joins, the PIM joins, will just be sent whatever the IGP is telling it to do. And so again, PIM is protocol independent multicast. It's independent of which IGP you're using. It relies upon the IGP, whatever one you happen to use. And so as fast as your IGP can recalculate and converge, your multicast will converge as well. So there will be a little bit of a hit there. There will be some time where you'll have to recalculate and reconverge. But it works, and it works well. You can also take this and make it even a little bit more involved in something that we refer to as priority cast, where you can take these two sources and you can have the same IP address but make one a longer mask than the other. And so the more specific one will win and will take priority over the other one. That's an option that you can use as well using your IGP in your network. So you can't have sub-second failover in this case. I mentioned it's IGP reliant. It's nice because you can move these sources freely throughout your network because they're all using the same IP address. And there's no vendor proprietary syncing that's necessary between the sources. All right, well, let's say that another way to provide some additional resiliency in your network is that let's say you're not using RCPTE in your network and you don't want to add that to your network. People that are using RCPTE understand the benefits and they're able to use it to re-optimize around the network. Let's say we want to provide fast rerouting for your IP network. Well, that's been available. It can also be available for your multicast traffic to quickly route around failures. One solution that some of you may know, Dino Farinacci, he's spoken many times at NANOGS. And he has this proposal. I think he's even presented this at NANOGS before. I know he's done so in other forums. And that is to provide a way for multicast-only fast rerouting. It's a make before break solution. You don't have to configure it on all the routers. And let's take a look at it. Here's the concept. So we have a source on the top and a receiver on the bottom. And we have two equal cost multicast paths to get towards that source. So the way multicast PIM handles that is when it has two neighbors of equal cost towards the source, it needs to choose one path for reverse path forwarding. It will choose the one with the highest IP address. That's how it's specified, and that's how it works today. So the receiver is going to join that source, the join path. Let's say router C has the higher IP address, so that's the router it's going to send its join to. But when you're using, and these routers have their outgoing interfaces leading towards the receiver, and the data is sent on the right-hand side of the network. When you're running multicast-only fast rerouting on that router D down there, what it can do, and this is unique, is it can send a join on the alternate path. It knows it has a redundant link leading back towards that source, so it can send a join on that path as well, which is what we don't normally do with PIM. So router A will be sending traffic on this alternate path as well. So it has two interfaces leading both down towards this receiver. So router D is getting the traffic on both interfaces, and it's only forwarding one. So that is nice if we have a failure on the left-hand side, and you're able to, or either side, and you're able to quickly get the traffic from the other. People may say, you know what, we have wasted bandwidth on the left-hand side. And that's true, you do have wasted bandwidth. You have two streams going on two different parts of your network. Unless you have receivers over there on the left-hand side, then it's not wasted bandwidth. So when a link fails, you'll make a local decision very quickly to accept packets from B, and the packets are already being received, so you can quickly fail over. So that will provide a good experience, a good quality of experience for the user of an IPTV stream. I mentioned multicast is very reliant upon the underlying IGP for its convergence, its failover, because again, protocol independent multicast. And so there's a variety of things that reconvergence is a sum of. You can get some pretty quick reconvergence. PIM needs to do its thing, the IGP needs to do its things, but so you are limited to a certain amount of speed because of what you have to rely on just with multicast itself. So it's nice if you can engineer the network to help give you some assistance there. You could provide some backup tunnels. So let's say router 2 is a router that we want to engineer backup paths around. So in event of a failure, we can quickly get that traffic off to these different receivers. We could do that if you have a lot of bandwidth on the lower part of your network, because in this case, you would have to engineer multiple tunnels for the different receivers. And so you can hammer a certain part of the network if you don't have a certain amount of available bandwidth. So typically what we recommend is having a platform with high availability. A router that has two processors, an active processor and a standby processor. And just focus on this node itself rather than trying to engineer around the network. Let's just make it so this node itself doesn't fail, so we don't have to even worry about trying to re-engineer around it. So how can we do that? Well, what happens is if you have an active processor fail, the standby processor takes over. What does that mean for PIM? Well, it's still the same IP address, but we need to quickly get this standby processor to be able to get the joins and the traffic and set up neighborships with its PIM neighbors, instead of having to wait for the next periodic join to come from the neighbors, which could take, a minute or more to get that. So we need to make this quick. So there's something that was specified in the PIM draft and that is a generation identifier, a gen ID. That's something that we can now send in a PIM hello message to identify a particular process. So when an active processor takes over, it's going to send out immediately this PIM hello with a new generation identifier. So when the PIM routers over there get that, they'll see it from the same IP address that they already know about, but they'll recognize it as a process restart. So they'll immediately send in their PIM joins so that we can quickly refresh state on this new processor. So that's a very quick way of allowing this backup processor to quickly get joins and get its neighborships built up and continue on with what it was doing before. Something else we can do in our network is we can establish multiple topologies. Again, we're not talking about RCPTE. If we're using RCPTE, we already have a way to have multiple engineered tunnels from our head end. But if we, in a non-RCP environment, want to do similar things, there's a variety of technologies out there to allow you to have multiple topologies, including using MBGP, multi-protocol BGP, which I know many of you are familiar with. Some people will refer to it as multicast BGP, but that's not correct. But there is a multicast component to it. You can set up static routes. You can actually use a method of multi-topology routing. And so let's just really quickly go through this. I got like 25 minutes, so let's fly through this. So MBGP, multi-protocol BGP, it's been defined for many years. It's being used in networks. It's being used in the internet today so that you can influence the path that your multicast routing will take. So if you have a BGP route and an MBGP route, which is MBGP is a different routing table, and they're the same prefix, you'll prefer the MBGP route. So you can influence the RPF mechanism of your multicast to go where you want it to go. It does that by using these address families. And within these address families, you have sub-address family information. Sub-AFI of 1 is used for unicast, and sub-AFI of 2 is used for multicast. So how this works. So we get an update from a peer, a BGP peer, with an address family of 1 for IPv4 and a sub-address family of 1 which specifies unicast. So we know that that update needs to go into my unicast table for unicast forwarding. If we get an update with a sub-address family of 2, we know that that's to go into my multicast BGP table used for my RPF lookup for my multicast traffic. So I can influence that to go where I want in my network. That's been used for many years. How about multi-topology routing? That's a technology that's been around for a while as well. Let's say that within your network, you want to have a certain part of the network be there for your voice, another part of your network be for your video, maybe another part of your network for just your regular data, internet, whatever. You can use multi-topology routing to specify that. So that's something to consider as well as you're architecting your networks for IPTV. I've mentioned live. You can use MTR, multi-topology routing for live to have different parts of your network sending the same stream. Because typically with multicast, you'll just use one part of your network for your stream. The RPF mechanism will just choose one side or the other. It's not going to choose two. And so there are some things you need to do, either using RSVPTE to have two different diverse paths or multi-topology routing. Or you can even use live temporal separation in the application as well by delaying a copy. So this is what live is with path diversity. The source is sending, or multiple sources are sending the same data into your network over diverse paths. It's important to have diverse paths, because if you're sending over the same path and that fails, that doesn't buy you anything. So there are a lot of alternatives. It is really important for multicast to have that quick failover. Again, you need to have a good quality of experience for your customers. And again, you can really have zero packet loss If you can afford to have multiple streams in your network saying the same data, then you can have a hitless mechanism for your traffic. Even in ring type topologies, which you see a lot in the cable industry, it doesn't necessarily have to be in the ring topology a diverse path. You can have that overlay a little bit. So for instance, you could have two streams, one sending it clockwise, the same stream is being sent counterclockwise. And so if there's a failure, you'll have both sides receiving that traffic from either direction. So that works as well, and that's being used. For those of you that like the layer 2 side, you can also set up pseudowires so that you just have Ethernet going from R3 to R4. It looks transparent. And you can also use pseudowires, and you can make it so that it has the 50 millisecond failover by injecting it into an RCP-TE tunnel. And so that will give you that very quick failover if you are using pseudowires. I know I'm going through a lot of technologies. You're going to probably have to look at this a little bit, but these are all things that are being used and things that you need to consider. So how about PIM? So many years ago, we were just very paranoid about non-RPF traffic hitting a router or a switch, just getting hammered with non-RPF traffic and having to drop that, and usually using the route processor to do that. And so because of that, we kind of did things backwards, where we break before we make a new path. So in this case, if the link router A fails, what will the router C do? Well, it's notified that the RPF change, the reverse path forwarding, has changed from router A to router B. So what it first does, it's going to send a prune to A. There's no traffic that's being received. We got a failure going on here. People are freaking out, not getting their channels. It will change the RPF over to B, and then it will send a join to B, and then it will get the traffic. So there's a delay there. What we should have done is do something that we refer to as make before break, and this is something that's being worked out in standards as well. And that is, let's say in a perfect environment where we're trying to fail over now. Router A, that link is back up. It's receiving the traffic. And so the unicast topology tells us that our reverse path forwarding should now be router A. So we're not going to do a break before make. We're going to do a make before break. So we're going to send a join to A. We're still receiving the traffic from B. Everybody's happy, getting their fashion TV or whatever. And then we will send a join towards router A. The traffic starts coming in from router A. Once we're receiving the traffic from router A, then we will send a prune over to router B. So we'll make sure that that gets sent in from the alternate path before we break it. So in that case, that's what we want for IPTV. We want to be able to make it before we break it. So that's something that we're working on. How about path selection? We're just going from one bloody topic to another. So we've got these variety of regions. We've got these cores. You've got these 10 gig links. Maybe you want to send 2 gigs of multicast traffic across those. Using IGPs, you can, using cost, you can engineer to have that go where you want. With multicast, it's not quite as easy. We want, with unicast, you can load split it quite easily. With multicast, you could be having it sent on multiple links where you don't want it to have it. You don't want it to be sent on multiple links. You want it just to be sent on links that lead to where the receivers are. So there's some things you can do, like using multi-topology routing that I already mentioned. You can use RCP tunnels to help out with that. But kind of what it all boils down to is the effect of multicast on equal cost paths. What happens oftentimes is you have this polarizing effect. So right here, let's take a look on the left-hand side. Router 1 and router 2 and router 4 and all the other routers, they're all going to use the same algorithm for the reverse path forwarding. Router 1 makes a certain decision that I'm going to use this link to get back towards the source. Well, router 2 is going to use that same thing as well. And so you can have a polarizing effect on your network where the traffic is only going on certain parts of your network and the other parts of your network are not even being used. In this case, the link between router 2 and router 5 and router 3 and router 6 are not even being used. And so that's not good. We want to be able to utilize those links as well. We want to be able to see something like on the right-hand side to be able to have all the links being used. We also want to be able to do on an equal cost multipath. If we have a failover on the same Ethernet wire from one over to another, we want to be able to make sure we don't affect the streams that are already occurring, because the algorithms today typically are just using a hashing mechanism. So those streams could be affected as well. So we do have solutions, CLI-based, so that you can engineer it so that you are able to take advantage of all the links in an equal cost multipath environment. Again, you can use traffic engineering to do it, and it works quite nicely. Statically configured EROs. And MLDP is very similar to PIMs, where you are needed to take advantage of certain topologies and multi-topologies to prevent that polarization from occurring. How about emission control? All right, so in regular broadcast video, you got a 1 here, look to the 1 on the right. You got these IGMP joins going to the DSLAM. And the DSLAM is just statically joining all these channels. So when an IGMP version 3 join comes up, the DSLAM will forward it where it needs to go. Let me skip down to router, number 3 here, real multicast. Real multicast is dynamic routing across the whole path. We got the hosts requesting a particular stream using IGMP version 3. Once those joins are received, it signals the network to start sending down the traffic to the DSLAM. That's real multicast. In switched digital video, we can actually oversubscribe a particular link with saying that we have, and there's a slide coming up as well, but we can offer more channels than we actually have bandwidth for on a particular link. Having static tree and relying on joins as well. So this is how switched digital video works. Let's say that we've got a certain amount of users on coming off of a particular DSLAM. We've got 300 available channels. And we can do some statistics and just monitor what's being watched by the particular customers. So we can say, okay, well, we've got 50 programs that are always being watched. They're the big popular TV channels. So we need to make sure that we have enough bandwidth for those popular channels. Out of the remaining channels, there's never more than a quarter that are being watched. So we never need to have more bandwidth than 125 channels. I know we're offering 300, but we really only need to make sure that we have bandwidth for 125. And we could have dynamic joining towards the core, although again, today, typically that's just static joining towards the core. But we need to have some insurance. I know that we're oversubscribing this link, we're using switched digital video, but we need to make sure that in the event we do have more content than bandwidth available, that we need to have an insurance policy to make it so that we don't hammer that link and cause a problem for the existing users that are happily getting their traffic. So we need some emission control. We need to avoid congestion. There is multicast emission control available in routers that allow you to do this based upon CLI configuration. There's also discussion on using RSVP on the client side to more dynamically make this possible. So you can have emission control from the client side. That'd be nice to not have to statically configure emission control on certain links. You could even set certain policies beyond the emission control. So let's say that we have 3 content providers and we're the service provider, and we want to set a certain policy. Well, okay, we're going to give content provider 1 250 megabits per second. Actually, we'll give all the content providers an equal share of 250 megabits per second. That's what they have available to them. And maybe we'll leave over the other 250 for voice or the internet or video on demand or whatever. So you can set certain policies using multicast emission control as well as making it so that you don't oversubscribe the link. There's a protocol out there that's also making this more dynamic. It's called the Access Node Control Protocol. It's a way to, from the access node, control the DSLAM dynamically, letting the DSLAM know of the white and black list, the go and no-go lists, so that the DSLAM will know which interfaces to allow, which not to allow, based upon the available bandwidth. So you can preserve your network dynamically using ANCP. How about channel changing? It's very frustrating when you go to a hotel and you switch channels from one to another and you have to wait. It seems like a half hour, but it's maybe 5 seconds from one to go to another. And you would think maybe it's the network. All that we've talked about today, we're trying to prevent that channel changing and failover from occurring. Again, we want a good quality of experience. And so what's making this 5 seconds or whatever, 4 seconds delay from one channel to another? That's annoying. We did have a legacy problem that we don't really worry about anymore with IGMP version 2, where when you go from one channel to another, you have to send a leave into the network. You're leaving this particular stream and you want this new stream, then the router had to send a query. Does anybody else want that stream? If not, then I'll stop sending this stream. And so there's a delay going from one channel to another. That's obsolete with IGMP version 3 because there's explicit tracking of all the receivers. So if you receive a leave for one, you already know whether there's no other receivers out there that don't want that stream. So you can immediately withdraw that and go over to the next one. So that's one side of it as well. But really, what it gets back to is this group of packets. With these new encoders, the group of packets are getting larger. So sometimes you have to wait for the next darn iframe before you can change the channel, before you can get the new stream to come in. And so that's really where we need to focus our efforts on, is just to really try to prevent failure from occurring. Because the network is with all these mechanisms that I mentioned, it's going to quickly get that stream coming into you. If you do have a failure or whatever, it's going to come in really quick when you're going from one channel to another. It's really waiting for the next iframe, which could take several seconds. So, and I think this may be the last slide. There is some solutions out there for very quick channel changing, and that is retransmission mechanisms out there. So you could have a device, we call it a video quality experience, over here it's homed in there with the aggregation router that's receiving the same multicast streams and it's buffering them. And so a set-top box that's running software that you can get today will be doing signaling with this VQE device. So when it's doing its channel changing, it can quickly say, okay, send me the last iframe, so I don't have to wait for the next one. It can get that group of packets really quickly. And so that VQE device will very quickly send that off to that set-top box, so it doesn't have to wait for the next iframe. The VQE box is already buffering it. It's able to send it on its merry way. And so that is a really good solution for fast channel changing. And so it's something that you may want to consider in your network. So in summary, there's a lot to summarize. It can get overwhelming to go over everything I just described over the last hour and a half, but there's a lot of things to consider. Primarily, I hope that on the transit side, you've realized the importance of choosing your transit protocol well, whether that's SSM or MLDP or point-to-multipoint RSVT. There's strengths and weaknesses of all of them, and so just be aware of those. And it's really, again, all about getting a good experience for the user. So that's a lot that I just slapped at you guys. Any questions now or before dinner? Yes.
Hi, pardon me for having my mouth full, Rob Seastrom.
That's fine. Either way, and speak up a little bit.
Do you have any words of advice for those of us who are looking at building something like this and want to build it right and build it once and are having a hard time finding set-top boxes that speak IPv6 and ONTs that speak IPv6? Okay.
So, not really. I don't really have too good advice. So if you have a network that is IPv6 and set-top boxes that are not IPv6 capable, that's really something that maybe people in this room actually can offer advice with, because that's just, there's a lot of solutions that go beyond multicast that allow for the capability of, tunneling mechanisms and all that to get that.
Getting the packets to the edge isn't the problem. It's that the equipment that you would hang on at the edge seems to just sort of not be there yet.
Okay. So
and I've been dealing with vendors round and round and round for the past 9 months, and I'm wondering if there's something I'm missing here, or if people are just asleep.
Yeah, I don't think there's nothing much you're missing. I'm sure there's a variety of discussions on V6 at this forum. Actually, that's I don't know if you guys have anything that you want to chime in on, but I don't have any good advice for you. Sorry, it's just the whole topic, and it's the whole thing of whether we really need the demand for V6. From my perspective, in the U.S., it just isn't there yet. I mean, we're just not. It's not. I'm coming from a vendor, and we're doing our best, but it's just maybe it's not a priority that we need to have. But we've had V6 in our capabilities for our routers for a long time, but there's a lot of devices beyond routers. So.
There's a lot of issues like IPTV, let alone adding V6 to the mix.
Yeah. So it was just mentioned that there's a lot of issues with IPTV, let alone adding V6 to the mix. Although, as I mentioned at the outset, we have some successful deployments in Japan that's using V6 with IPTV, so it's working well. But they obviously have devices end to end, all those devices that are able to support V6. So, anything else that I can't answer? Yes.
Just an extension of that. SSM.
Yes.
You've spoken a lot about that. Are you seeing that?
A little closer to the mic.
Can you hear me?
Yeah, that's better. A little louder. Yeah. Sorry, it's so short. It's for me, I guess.
Are you seeing that SSM support is sufficiently deployed now that you can depend on it, particularly in networks where you don't control it fully end-to-end, including CPE equipment?
Yeah, the answer is yes. SSM is widely deployed. It's been in our routers and other vendors' routers, all vendors' routers, I'll go out on the limb and say, for many years. Really what we've been waiting for a long time is on the host side. It's a lot easier to upgrade a router than it is to upgrade millions on the host side. But there's quite a lot of stacks out there that do support IGMP version 3, because that's really the question you're asking, is V3 support on the host side. Set-top boxes, maybe not as much, because that takes upgrading the set-top boxes of the customers. But the answer is yes. The router's been, on the network side, it's been there for a long time. The host side, it's getting there. There are some workarounds like SSM mapping that allow you to work around that from the network side.
What's your perspective here with, you're talking a lot about IGMP and basically growing the multicast out, but what's happening is we're finding in the IPTV deployments now, people are starting to, it's more VOD, we want it now, we want it when we want it, as we want it. So that's begging net PVR and more unicast.
More unicast, absolutely. That's right.
And so, yes, there's going to be some when the NFL games are on or when CNN's always going to be streaming, but with MPEG-4 and the bit rate and the amount of bandwidth we're needing for those streams is diminishing, but we're having more and more of an increase for the unicast type of functionality.
Okay, so that's...
I mean, where do you guys see that going?
Yeah, that's interesting. Yeah, so I haven't heard that. So if your network is being more and more utilized by video on demand, some people are using multicast to pre-provision the network, the streams. But of course, otherwise you're using unicast because it's not live streaming. Live streaming, you use multicast. So, yeah, in that case, then it's even more important to do all these emission control device capabilities to be able to make it so that the real streaming goes, and that will affect your real streaming. If you got a lot of video on demand unicast traffic on your network, your real-time traffic is going to be affected. Get more bandwidth, get more optical links. I mean, yeah, it's a usual answer.
Could you also just talk about
what time?
where's that standard? Is that a standard yet?
Okay, so this will be the last question because I know we need to get out of here. These guys are doing it. So, want to know where VQE is? It is something that's available today, so you can use that. As far as standards go, it's not, as far as I know, a standard. because the name itself is a Cisco name, the retransmission is something that's been considered before. We think we got a pretty good way of retransmitting now. So it is definitely a proprietary method of allowing retransmission. So I don't know if we have actually any plans to standardize it. We'll see actually how it goes. So good question, but it's available today if you want it. I don't want to sell my own technology here. That's not what this is about. But thank you very much. Thanks.